I think the main thing to understand today is that there's data every place. And that goes from, for example, just purely in the business world, there's tremendous amounts of data that are collected by companies all the time. An example of that is Walmart, the big retail company, has stores all over the world. And as you know, in a modern store, when you run things through the scanner at the checkout counter, every single item that you buy gets recorded. And that all gets collected and from all the stores gets collected together. And it creates huge amounts of data. And companies like Walmart, part of the reason they're successful is they mine that data to extract information, predict things like if the weather patterns are this way, you know, if there's cold weather in Iowa, then you better make sure that you have enough snow shovels at the store. And retailing has become a very data-intensive business of trying to collect information about people, and each little piece of information is sort of minimal. It's just a particular item at a particular cost at a particular time and place. But combining all that information together gives them tremendous insight. Doing image processing on all the data they collect. In fact, there's this class of digital telescope they call a survey telescope that just continuously scans through the sky every night. And they're building one on a mountaintop in Chile that's going to be collecting data just all night long, every night. And a lot of the science of astronomy is looking at the patterns, not just of the individual images, but how things change from one time period to another. And again, there's been many important astronomical discoveries have come just by taking all this data and being able to make use of it. There's a whole movement afoot in the world of humanities to understand patterns, understand things like how language use has changed over time, historically, or geographically. And so all of this is driven by the availability of data. So why is there so much data in the world? There's a couple of reasons. One is that it exists. So with something like a sales terminal at a store, that gives an immediate method to collect digital information. There's huge amounts of data in this world that's created in digital form, and with networking technology, it becomes possible to gather that information. And another big driver of it is actually the storage technology. In particular, magnetic disks have grown in their capacity at an unbelievable rate, faster than the rate, the so-called Moore's Law rate for the improvements in computer memory or in microprocessor capacity. And this has been a trend overall, so that in many ways, even though we're generating huge amounts of information, our ability to collect it and at least store it in some form has also increased. Just as a reference, the US government maintains what's called the Library of Congress, which includes every single publication at least that comes out in the United States. But all those books, if you were able to digitize them and encode them, would only take around 20 terabytes to store. So literally on 7 disk drives, so this much space, you could hold sort of all of the information that's in at least the text part of the Library of Congress. So 3 terabytes is a huge amount of storage, and it's really very impressive that you can get it. But what am I going to do with it? Well, my model and what sort of inspired me and many others to really look at this is what Google has been able to do. And Google's essentially been able to make a multi-billion-dollar business just purely out of information. It doesn't do that by going off and looking at the internet just for you. What it's done is it's gathered into its servers a copy of every single web page it can find on the internet. And then it's pre-processed a lot of that to get it organized and figure out what words occur in each document. But even so, with your particular query, they're starting up several hundred processors worth of computing going on. Looking at the set of web pages sums to something in the order of a few hundred terabytes. The exact number is not really known by anyone outside of Google. But some very large amount of storage. And according to a paper they wrote some years ago, it was about 10 billion clock cycles worth of processing. The other part of it that's a big part is that the response rate back to you is well under 1 second. And they've learned, and part of Google's success over its predecessors was they learned that if people get a response measured in a few hundred milliseconds, then they'll keep using it. And if it's slower than that, maybe it takes 5 or 10 seconds, they'll get tired and go away. One other part, and I'll get into this, is they make money out of this, but they don't have to make much money off of you to make a lot of money overall because they're serving so many people. So going on with Google again, and people criticize me for talking too much about Google, but it is very impressive. Like I said, they're operating some of the world's largest data centers. They built, this is a picture of one they built in Oregon, in a part of Oregon that has a large river flowing past it. And so they generate hydroelectric power. So it's very inexpensive electric power. So Google used to be very secretive about how they actually built their machines. But more recently, they actually made some YouTube videos giving tours of some of their data centers. So if you're interested in this kind of thing, I recommend you look at these. But in particular, they sort of build their computers. They put them into boxes that are sort of the size and shape of shipping containers. Then they plug up a very large electric cable, and they have to plug in a water supply to keep the things cool, and then a very large internet cable. But that's really what their computer systems are. And if they periodically, if they want to replace the computers, they just get the truck and they pull away one shipping container and put in another. So they're building at the scale of really massive complexity. Much bigger, for example, people brag about their supercomputers and how big they are. In terms of total computing power, what Google has built dwarfs anything anyone's built as a supercomputer. Different type of computer, but very large. Just a higher speed version of that. And the machines themselves aren't in desktops, obviously. They're built into these little boxes and then put into racks of computers. But in terms of what the computer is pretty much the same technology as is used in desktop machines. And that's been one of Google's successes, is to, by using the same sort of commodity commercial technology that millions of consumers use, the price per unit is extremely low. And so the cost effectiveness of it is very high. It's a little like buying a regular car versus buying a Formula One car. And they make it up by lots of computers as opposed to a small number of very fast computers. So really then the point I'm making is, well, I'll move on. But a single node, what they call a node, so a single processing node in their machine, consists of 1 or 2 microprocessors and 1 or 2 disk drives, and then it has some memory associated with it. So one node then is about 2 terabytes worth of disk storage and some amount of RAM. And then they assemble that into a rack with cables connecting it all communication-wise. And so out of a rack's worth of machines, you get 80 machines there. And that gives you a total of about 160 terabytes of storage. And then they'll fill up a room or a shipping container full of racks and get out of that, here they're saying 30 racks, getting you 4.8 petabytes. So that's 4,800 terabytes. And so the challenge then from a systems point of view is, how do you take something like that as a piece of hardware and make it usable for any kind of storage task or data processing task? People in this room will know the answer to this, but it turns out the most valuable word that you can, so by the way, they sell these links by an auction process that's going on all the time. And so you as an advertiser pay for certain words that if a person types it in as a search term, your link will show up on their web page. And so it turns out the most valuable word in all of the world as a result is mesothelioma. I usually ask that as a question, but I know there's people in this room that know the answer to that, so I won't show it. I was just reading, there's only about 2,000 cases in the US per year, so it's not a common cancer, but it's a very deadly cancer. And the people who have it are very unhappy, and so they want to file a lawsuit against, usually they worked in a factory where there was a lot of asbestos around, and they've had this permanent damage as a result. And so there's a very lucrative business among lawyers filing, at least in the US, where we like to do lawsuits, for people who have been victims of mesothelioma. So as a result, the law firms that specialize in these cases are bidding very high prices on Google, because if you can get a customer, especially as part of a class action lawsuit, you can make a lot of money. So that's sort of their model. It's not true that it averages out to about 5 cents. And I argue on the other side, that's pretty cheap. If you have access to all the world's knowledge for just 5 cents per query, that's a fairly reasonable price point. And it's part of Google's success is they're able to hold their costs so low that they can pay for it with advertising. They don't have to charge you a subscription or some premium membership. One other example I'll use, though, actually, and so let me mention many people use the term cloud computing to refer to this type of computing. And I find that that term itself is very ambiguous, because it means many different things. And so the way I view it is the sort of term cloud computing to many means basically what you'd call hosted services, meaning that there's something like an email account that you have via Hotmail or Gmail or one of these, where you as a user or a customer, you don't know where that email is stored, and you don't really care. It's just off in the cloud somewhere. And there's a growing business of those kind of services. And that's all well and good, but to me it's not the more interesting part, just doing these. What I like to describe what this kind of computing is a cloud of much more serious type. This is a tornado, where there's a massive amount of data stored, and I want to be able to harness the computing power of hundreds of processors together and solve very difficult problems. So one of the impressive results that came fairly early on with this, and again I go back to Google, was in 2005 competition. So this goes, the US National Institute of Standards Technology has a competition every year for machine translation from one human language to another. And each year it's a slightly different combination. But in 2005, it was, they had two competitions. One was Arabic to English, and the other was Chinese to English. And both of them involved taking news articles in the source language and translating them using a computer into English, and then doing a comparison, a statistical comparison of how well that computer did to some expert human translators. A score they call the blue score, which is, and what you can see is this was the first year that Google had ever entered it, translator, which is impossible because they have 4 different human translators. So anyways, this was about 0.45. And Google came in as a first-time entrant and was substantially above what everyone else had been able to do. And not just in a sort of numeric sense, but qualitatively too, a significant step forward. In particular, these translations involve statistical methods, and so they'd used some existing text, things like the minutes of the United Nations, where there's parallel text in multiple languages. They trained it using these models of text data sources that consisted over 1 trillion words of training information, which was more than an order of magnitude more than anyone had ever tried before. And similarly, they had an entire cluster, one of their clusters devoted to it, of about 1,000 machines that they used both for doing the training and for doing the translation during the competition. And nowadays, many of you probably make use of the translation tools that you can get online. But this was one of the first real breakthroughs, showing that if you just take the existing algorithms with very little change and you just simply step up how much data you use, it made a qualitative difference in the quality of the translation. This is where I first got introduced to the realities, because our language translation people came back from that competition and say, you're the dean, you have to find us a 1,000-node cluster so we can compete against Google next year. So that's a sort of story of, as I said, the good news is that storage is relatively inexpensive, and every year you can buy a bigger disk drive for the same or less price than you could last year. And that will continue to scale. What hasn't translated nearly as, scaled nearly as well as the speed at which you can get information either on or off of a disk drive. That's changed only very slowly over the years. And that's a sort of fundamental aspect of the technology. So as a result of that, you can think of a disk drive now as almost like having captured this huge amount of data connected by a very thin wire pipe to the rest of the world. In particular, if you just said a simple task of taking all the data on a disk drive and reading through it for whatever reason you want, or writing to it, it takes several hours to do, even with the sort of best disk drives you can buy. It's a couple hours per terabyte. So scanning that 3 terabyte disk drive will take you a good fraction of a day. So that raises a challenge that if you want to be able to really do data-intensive computing, then you can't put all your information on a single disk drive. You have to spread it over a number of disk drives and build one of these cluster machines that gives you multiple disk drives, all with parts of the data stored and with computing power associated with it, and networking that connects it all together. And then somehow you have to program this machine so that it will do the kind of work you want to do. One is, as I mentioned, the main interest here is how much data can you manage, can you store, and can you process, not how fast your computer can run, say, in terms of calculations per second. Another is, how are we going to program these machines? Do we have a way to program them that is not the sort of low level, I have to write code that will run on each processor and make the thing work together? A model that sort of raises you up at a level that you can think about what problem you're trying to solve more than what kind of machine am I solving it with. And then the other, which is in some ways the biggest challenge, is what do I do when things break? As soon as we have machines on this scale, things inevitably break. So for example, a typical disk drive has a lifetime of 3 years, which means that if you had 1,000 disk drives, you'd expect every day to have one of them go bad on you. And we make the machine still run reliably, even though the individual pieces of it might be failing on us. So one programming model that's proved very successful for data-intensive computing, again, it came out of Google, is called Mapreduce. And I'll give you a brief description of Mapreduce and tell you how it gets used in practice. But the interesting thing about it is normally programming a very large parallel system is a lot of work. So the code you have to write, the sort of basic code you have to write are 2 functions. One is called the map function, and the other is the reduce function. So let me give you an example from sort of the most elementary Mapreduce. So the first book I had to learn to read is the book they call Dick and Jane. The idea of Mapreduce is we first do a map, which means we extract out of the document all the words that occur in that particular document and a count of how many times they occur. And so the word itself is what I'll call a key. It's a way that sort of tags the information you want. And then the count of how many times it occurs in this document is the value. How many, it's something associated with that key. And then what happens in between is all that information gets sorted by keys or reordered so that all the messages or entries here with the same key get grouped together. And then you write a function that is the reduce function that will take all the information with a given key and combine it together. In this case, all I have to do is sum up the counts for it, and I'll get the word count index. The idea of it is twofold. One is to take a cluster computer like I described before. And the other part that Hadoop gives is a Mapreduce programming environment so that it can execute these Mapreduce programs based on the data that's stored in these files, on this parallel files. So Hadoop, as I mentioned, is an open, I'll talk about Hadoop a little bit later. But the overall execution then of as I mentioned, a typical program is a sequence of Mapreduces. And it will just, it'll break up your program into many, many tasks, which are just, each one is just to do a mapping for one particular document, or a reduce to do the reduction for one particular key. And it will spread that over these different machines, and each of them will read the files associated with the data, do the mapping, those values get combined and sorted, and then they do a reduce, and then the output from the reduce gets stored as, on the file system, so that you can complete the task in a few milliseconds instead of in a few hours. So the nice thing about this from a fault tolerance point of view is if one of these tasks fails, for example, as I mentioned, if a disk drive goes bad or something else happens, it's a very simple matter just to redo that part of the computation. So just to tell you about Hadoop, as I mentioned, it's an open source project that really was inspired by other work that was done within Google. And the idea of Mapreduce comes out of Google. But it actually was a project that for many years was largely driven by Yahoo, which of course is one of Google's competitors. And, but they decided to go a route of an open source project, meaning that the software is freely available to anyone to use. And they built a very large and successful open source community around Hadoop that, as I said, it started with Yahoo being the major driver, but since then has added many more companies, both large established companies as well as startup companies. So let's just look at how this compares to other types of computing, and why is there something different about data-intensive computing compared to others, uses of data in the information processing world. And so that's been a big use of computer technology for many years. And that's a very different type of work, because first of all, each transaction is a relatively small amount of computation, but it has to be done perfectly. Because if you're transferring your money from one bank account to another, it's very important that that money doesn't get lost or duplicated. Right? Somebody will be in big trouble otherwise. And so there's a lot of concern of what happens if in the middle of making that transaction the network fails or some other part of the system fails. We have to make sure that we don't have an inconsistent state between the two. And so there's been actually quite a bit of research over the years on how to do this. But it turns out from a computing perspective, what it does is you pretty much have to, the more copies of data you have, the more difficult transaction processing is. And so there's a tendency to limit how many copies you have and usually use higher cost hardware to give you the performance. And so we're in a very different world. As I mentioned, in a Hadoop file system, you typically have 3 copies of every file. And we're not trying to be nearly as precise in the transactions. Another sort of related technology are databases. And of course, most businesses make heavy use of database technology. And there's been a lot of misunderstanding and somewhat controversy between database people and the data-intensive computing people about the relative parts. And so again, a database is a fairly different technology in that its purpose is to store data and make it possible for you to retrieve it or else do some sort of analysis of that data. But it is a very different style, meaning that typically there's the data is in a very organized way, a very structured form, as opposed to something like a simple web page or a text document. And they're optimized to perform particular types of queries that are determined which ones are the most likely ones to use. And usually it's a proprietary technology for the software implementation. But these also do not tend to operate at the scale that we're talking about for data-intensive computing. There was actually an interesting blog post in 2008 by two very prominent database researchers at the early days of Mapreduce. And you see in red, the whole thing was, the tone was decidedly negative. But they claimed that all of this work was a giant step backward in programming languages that had already been done by database people years ago, and so on and so forth. The problem was, quite honestly, they missed the point, that they were thinking in terms of how does this look compared to databases, and really the two are solving very different problems that call for very different solutions. Since then, both these two have changed their opinion some and are much more balanced in what they'd say. So at the sort of left extreme is I use the SETI at home as a facetious example, but sometimes called an embarrassingly parallel application, meaning that there's just a large amount of computing and you can break it up into pieces, delegate it out to different machines, and have them each work independently. So SETI at home was a web browser, or screensaver that people had that was scanning through some signals from radio telescopes looking for the signs of intelligent life. Over on the extreme right, a lot of the theoretical work in algorithms for parallel machines is in terms of a model called the PRAM model that assumes you have as many processors as you could possibly want, and they all share a single global shared memory and have fast access to it, which is a physically unrealizable model. And there's many other models. For example, people are writing a lot of code using threaded programs or message passing. What I find interesting about Mapreduce is it works just fine for embarrassingly parallel applications, but it also lets you trend toward these other techniques that require more communication between them. And yet it's a fairly easy model to write programs in. So I think it's a part of a new movement to try and think about new ways of programming in parallel that are a little bit less, these models are very difficult to write code in. So, but I think Mapreduce in itself is only the start of a more general class of way of programming machines. So let me just present to you two sort of what I'd say are taking the ideas of Mapreduce and going beyond it. One is a research project at Microsoft called Dryad, where they take the idea of a Mapreduce, but they make it a little bit more fine-grained. They break it into smaller pieces. Where you think of a computation as just being a series of transformations on data, I've shown these as operations, that you perform over and over again to reach your result. You saw before the Mapreduce, the operations corresponded to first map and then reduce and then map and reduce. And these, they say, well, any code you want, but the purpose of this code is just to transform data. It's not to store it locally. And then they map these onto a machine and they schedule them, and if one of them fails, they can reschedule it. So at an implementation level, it looks much like Mapreduce. But it's a little bit, you can do other types of programming with it too. Another one, which is very recent, is a project by some of our machine learning faculty, one named Carlos Guestrin, that he calls Graphlab. And this isn't as mature by any standard as Mapreduce or even the Dryad project. And in fact, is only starting to look at the issues of how do you really scale this very large. But they seem to be on to something useful. And in particular, a lot of machine learning problems, it's a combination of it's both data intensive and requires a fair amount of computation. And so those kind of applications are not served very well either by pure Mapreduce or by a pure compute-intensive algorithm. You really need to combine them together. So what Carlos observed was that many of these problems, though, can be viewed as problems over graphs. And of the form that says, on each step, what I want to do is to do an update of some information for one part of this graph based on the values at its neighboring points. So an example I'll show of this is one that's called the Pagerank computation. So Pagerank was invented by Larry Page and Sergey Brin, who you might have heard of before. And in particular, they had a paper that they never really published about this, and they got a patent. And then when they went to form Google, the patent was held in the name of Stanford, and so they gave Stanford, instead of paying cash for the rights to this patent, they gave them some stock, which later Stanford sold for $330 million. So you could claim PageRank is a $330 million idea. But the idea of it is that you want to associate a value with each, imagine these were web pages. This is Carlos right in the center here. And so each of these is my personal web page, has some links in it, maybe to my friends. And so try and find sort of an ordering for which of these web pages is more important than others. And that will determine the order I'll list it in when I return search results. And so they came up with this measure called PageRank that associates a value with each node in a graph based on how many other links there are to it, but not just how many connections there are, but also how many connections they have and so forth. And I won't go into the details, but you can see this is the PageRank computation you get from here. And this is naturally a problem you can do in parallel. If you take this graph and divide it into pieces, then locally on each machine it can be doing this, this computation for its part of the graph. And then every so often it has to communicate between the different machines to let that, them all combine their work together. And then it's the job of Graphlab runtime system to worry about the rest of it. So just to give you, it is possible actually to do this using Mapreduce. You can essentially think of this formula I gave you as the map tasks then just generate all the information for each node, and then the reduce tasks do this addition and multiplication together. So it's possible to do it, but it turns out with Mapreduce, if you think about that execution model, you're reading all this data from disk, you're doing some computation, you're storing it to disk, and you remember disk drives are slow, so it's a very slow way to do it. So for example, they did a benchmark using a very standard graph that was sort of a graph of what the web looked like as of 2002, which of course is ancient history. Took several hours to do this computation. And with Graphlab, even in a fairly new version of it, they were able to do that same computation on a smaller machine in a matter of minutes. So even though, as I mentioned, Graphlab is a new project and still has a lot to work out in terms of scaling and fault tolerance, they're clearly onto something of being able to give performance for these machine learning problems that's very impressive. You can see all over the world there's more sources of data and more opportunities to use that. And we're really just beginning. I think a lot of companies in particular are just beginning to make use of the data that's available to them and doing things with it. But it requires a sort of different approach to computing than we've had traditionally. And companies like Google have sort of shown the result. And now there's open source systems such as Hadoop that's making that available not just to companies but to university researchers and people worldwide. And new projects like I showed, Bryant and Graphlab, that are sort of exploring other ways of doing the computation that I think over time we'll find more and more ways and better ways to do this type of computing. So thank you very much.